Okay, so welcome everybody to today's colloquial seminar. And so today's speaker is Dmitrii Pavlov, and he'll talk about realizations of input-output equations, rational, observable, and real.
Yes, thank you very much for the introduction and the invitation to speak here, and thank you all for being here today. So the things I'm going to talk about are based on two papers. The first one is with Gleb Pogudin, and the second one, a more recent one, is with Sebastian Falkensteiner and Rafael Sandra. It's almost the weekend, at least where I am, so I'll try to give a reasonably uncomplicated talk and just give an overview of the problem and of the main results without diving too much into the technical things. So I will indeed talk about the realizability problem, and this is a problem that originates, very interesting, great, in control theory. So the problem originates in control theory, and the setup in control theory is usually as follows. We have some system, and the system is really a black box. And this black box is described by a tuple of functions called x, and those functions depend on time. Now, this system can accept some inputs, which are described also as functions of time, so as a tuple of functions called u. And in general, in applications, we can control those functions, hence the term control theory. And then based on the state, so on the functions x, on the functions u, the system produces some output. And this is again a tuple of functions that depend on time. And those are functions y in the scheme. So in accordance with what I've just said, the variables x are called the state variables because they describe the state of our black box. The variables u are called input variables or control variables, and the variables y are called output variables. Now, control theory is a very applied area of mathematics. Most problems there actually come from real life. And in real life, we can make observations. And when we make observations in this setup, we can really see the control variables, the input variables, so what we impose on the system. And we can see what it produces. So we can see the u's and the y's. But we cannot really see the x's. So the system is really a black box for us, and the information about x's is not immediately available for observations. So we will consider systems of such form. And in this talk, for simplicity of exposition, we will consider that there is just one input variable, so just one u, and just one output variable, so just one y. Now, this is a picture. I've told you that there are some inputs, some outputs, but we are mostly algebraists here, I think, and we like equations. So it is reasonable to ask, how do we describe those things by equations? And there are, well, at least two nice ways to do this. The first one is to describe such systems by input-output equations. So I told you that we can really only observe the u's and the y's, but we cannot observe the x's. So we might decide to just work with the u's and the y's and try to find some equation that fits those two tuples of functions together. And it is indeed often possible to find such an equation. So to connect input and output variables by an algebraic ODE. Those are functions, they depend on time, so it's reasonable to assume that the equation we are looking for is differential. And indeed, one can find such an equation fairly often, and this equation will look like a polynomial in the y's and the u's and their derivatives. So this notation, infinity in parentheses, means that in our equation we allow not just the u's and the y's, but also their derivatives of time. And any such equation will be called an input-output equation of the system. Later on, we will see that there is a canonical choice. We can kind of choose the best input-output equation, but for now, just any equation will work. So this is nice because we can actually write this down fairly easily by using some fitting procedure from the data that is available to us from the y's and the u's. But at the same time, it is not really that nice because it does not give us any immediate information about the state of the system. So it doesn't tell us what the variables x are. So the second way to describe systems kind of solves this problem. So we can describe them by dynamical systems in the state space form. And those are systems of very simple differential equations. So here we have just one equation, but it can be of fairly high order and fairly high degree. And when it comes to dynamical systems in the state space form, all the equations are first order and resolved with respect to the derivative. So the first group of equations in such a system is x prime equals p of x and u. So this describes the evolution of the states of our system. And the second group of equations is essentially non-differential. So we just describe how the output y depends on the state variables x and the input variables here. And if you are a more discretely inclined person, you can think about this as a continuous time analog of the Turing machine. So we describe the evolution of the state and then we describe the output. So now we can consider different classes of dynamical systems, and those are determined by what kind of functions P and Q really are. So we can consider smooth functions, analytic functions, algebraic functions, rational, polynomial, linear functions, whatever. And in this talk, I would only like to consider rational P and Q, because when P and Q are rational, this system is essentially an algebraic object. All right, so this is nice because it describes the evolution of the states, but this is not so nice because it is not immediately clear how to write down such a description from the data that we observe. And because those two ways to represent the system, by input-output equations and by dynamical systems in the state space form, have their advantages and disadvantages, they kind of compensate each other, it is very reasonable to ask how do we go from one to the other. And now I would like to make this question more formally algebraic. So for this, I will need a piece of notation, which you have actually already seen a couple of slides before. So we have an element of a differential ring. So this element will be denoted by x, and a non-negative integer h. Then we will use the following pieces of notation. So we'll write x less or equal than h for the set of derivatives of x up to order h, and x infinity for the infinite tuple of all derivatives of x. And the ring of differential polynomials in x over R will be denoted by R of x infinity. So with this notation in mind, we can define the problem of differential elimination. So a couple of slides ago, I asked this question, how to go from an input-output equation to the dynamical system in a state space form and vice versa. So my talk is about the realizability problem, and this is precisely the problem of going from the input-output equation to the dynamical system. But if you want to formalize this problem and to write it down in the language of differential algebra, it turns out that the most convenient way to do so is to define it as the inverse problem of differential elimination. And that's the reason why I would like to spend some minutes talking about differential elimination. So in this setup, we start from a system of ODE in the state space form. So we've seen it before, right? X prime equals P of x and u. X prime is a tuple of variables, P is a tuple of functions. And now we only have one output because I promised you that we will restrict to that. So our only output variable y is some rational function of x's and u's. And we will now work over an algebraically closed field of constants k of characteristic 0. So being a field of constants means that there is a derivation on k and it's trivial, it sends each element to 0. So what we can do, there's a lot of symbols on the slides, but what's happening is really simple. So we have the system 1. It has rational right-hand sides, and we can bring all those right-hand sides to the common denominator. We will denote this common denominator by s. And then we can multiply all those equations by this common denominator s. And this will give us a system of polynomial differential equations, so we get rid of the denominator. And then we can generate a differential ideal by all those equations. And that's what's written in this line. I don't know if you can see my arrows, but the equation 2 on this slide precisely tells you what we are doing. We're taking all those polynomial equations that we obtained by clearing the denominator. We generate the differential ideal. So this notation means that we really take the differential ideal generated by those polynomials, and we saturate this ideal by the common denominator as is customary when things like this happen. So this is a differential ideal in the ring of differential polynomials in the variables x, y, and u. So in all the variables that appear in this control theoretic setup. And it is known that this ideal is prime. Now, differential elimination is about eliminating differential variables. And that's what we are going to do. So we'll take this ideal I sigma, and we will consider its elimination ideal J sigma obtained by intersecting I sigma with the ring of differential polynomials in Y's and U's. So we eliminate the axis, we eliminate the state variables, and we are only left with the output variables and the input variables. And this ideal will be called the ideal of input-output relations of our system. And it is known that when there is a single output variable y, this ideal is almost principal, in a sense that we can pick one differential polynomial that will really entirely describe the ideal. Namely, we should take this ideal and take a look at an irreducible non-zero polynomial of minimal order with respect to y in J sigma. And it is known that there is a unique such polynomial up to multiplication by an element of k. And then what we'll do, we will take this polynomial, we'll generate a differential ideal with this single polynomial, and we will saturate it by the separand of this polynomial, so by the partial derivative of this polynomial with respect to the highest derivative with respect to y. And such an f will be called the input-output equation. So this is the canonical input-output equation I talked about. And due to this formula here, due to formula 3, this unique polynomial will give a complete description of all input-output relations of the system we are considering. So that's the process of differential elimination that allows us to go from a dynamical system in the state space form to an input-output equation. And now we are ready to define the realizability problem, and as promised, it's just the inverse problem. So as input, we get an irreducible differential polynomial over k in y and u's. And as an output, we'd like to produce a dynamical system in the state space form such that f equals 0 is its input-output equation. Or we'll just say that such system does not exist. In general, if we have some black box that relates some inputs and outputs, there is no guarantee whatsoever that it can really be described by such a nice dynamical system in the state space form. So this problem, as I said multiple times already, probably originated in control theory. And classically, people in control theory use analysis to solve their problems, and this was one of the problems that was treated analytically for quite some time. And the first attempt to restrict the class of right-hand sides of the dynamical system, so the class where p's and q's live, to rational functions and see what happens then, happened in the late 80s. And the first attempt to actually study this problem by using methods from algebra, or rather algebraic geometry, was made in 1992 by Christoph Forsman. So Forsman studied a toy case. He considered an input-output equation that has no inputs. So it's just an output equation. It only depends on y's. And he gave a very nice, very simple, and very beautiful somehow geometric criterion for realizability. And this criterion is based on the notion of the corresponding hypersurface. So let us take our irreducible differential polynomial, which is our input-output equation, the polynomial f. It depends on inputs and outputs, and y and u and the derivatives. And let's say that the order with respect to y is equal to h. Then we can, for a moment, forget that this is a differential equation. We can treat it as a usual polynomial and formal variables y, y prime, and so on, yh, over this fairly scary field. So we'll take the field of differential rational functions in u over k. We will take its algebraic closure, and we will say that this is our base field. And our polynomial f has coefficients in this base field, and its variables are the h+1 variables, y2, yh. Now, this is a polynomial over some fields in h+1 variables. Therefore, it defines a hypersurface in an affine space AH+1, and this hypersurface has codimension 1, so dimension h. And this hypersurface will be called the corresponding hypersurface of f. And I would like you to note that in Forssmann's case, there are no inputs. So this algebraic closure of the field of differential rational functions in U is really just K, because we get rid of U and then we close up a field that's already algebraically closed. So in Forssmann's scenario, this field is just K, and we are looking at some hypersurface, so an algebraically closed field, so basically over C. And Forssmann's theorem is really remarkably simple. It says that the equation f equals 0 is realizable by a rational dynamical system over K, if and only if the corresponding hypersurface is unirational, which means that we can parameterize it by rational functions. So this is remarkable for a fairly simple reason. We go from a differential equation to some hypersurface that kind of forgets about the differential structure of our equation. It doesn't care that YH is someone's derivative. And we look for the parameterization, for rational parameterization of this corresponding hypersurface. And then Forssmann shows that there is a fairly simple way to recover a realization, so a system of differential equations that corresponds to this parameterization. So I will not talk about this right now, about how to do this, but this really is just basic linear algebra. So we have this wonderful result, but the setup is also very simple. There are no inputs, and the field we are working on is algebraically closed. So this choice was made because we want to relate this problem of realizability that comes from control theory to something in classical algebraic geometry, to parameterizing hypersurfaces. And classical algebraic geometry, of course, works at all, only over algebraically closed fields. And therefore, Forssmann already in his paper in 1992 poses two questions. First of all, what happens if there are inputs? What happens if f depends on u? And the second question is what happens over R? Because as I said, people in control theory are usually very applied, and for applied people, real numbers are often better than complex numbers. And I would like to tell you what happens in those two situations. So in the paper with Gleb Pavlov, we try to answer the first question, namely what happens if there are inputs. And in the paper with Sebastian and Raphael, we try to answer the second question, what happens over R? So let's now discuss those two questions in order as they appear. So let's consider, as promised, single input, single output systems over still an algebraically closed field of characteristic 0. And we will start slowly. We will only allow our equation to depend on u, but not on the derivatives of u. So we allow arbitrarily high order with respect to y, but the order with respect to u has to be 0. Then the equation p equals 0 has a rational realization if and only if there exists a special rational parameterization of our corresponding hypersurface. Namely, we want almost all of the components of this parameterization to be defined over K, and only the last component to be defined over the field of usual rational functions in U over K. So in principle, in the definition of the corresponding hypersurface, our base field is pretty terrible. It's an algebraic closure of the field of differential rational functions. So we allow some radicals, we allow arbitrarily high orders of U, but this all cannot happen if we want our equation to be realizable. We really want our parameterization to be very special and very simple. And then, so this kind of describes what happens when the order with respect to U is equal to 0. And the second proposition on the slide describes what happens when the order with respect to U of P is equal to 1. Then a very similar thing happens. You again have to have a very special parameterization. But now you allow two last components to depend on U, and the last component can even depend on U prime. But the first component has still to be independent of U in your parameterization. And now there is this condition in a differential condition which tells you that the partial derivative of gamma h with respect to U prime has to be equal to the partial derivative of gamma h minus 1 with respect to U. So this is the condition which kind of tells you that gamma h corresponds to the derivative yh, and gamma h minus 1 corresponds to the derivative yh minus 1. And yh is the derivative of yh minus 1. So now we cannot ignore this completely. We have to encode this into our parameterization as a special condition. And in principle, you could go on forever. You can make up proposition after proposition by increasing the order with respect to U. You could allow order 2, then you can probably see how it goes. we would have three last components that can depend on U. The last component would also be allowed to depend on U double prime. And there would be some more differential conditions that tell you that the last component is the derivative of the last but one component and so on. So the reason it's not on the slide is because when the order with respect to U equals 2 or is higher, it is almost impossible to do anything algorithmically. So it is impossible to, it's very difficult to actually solve the realizability problem in general by using algorithmic approaches. And what motivated us to do this is actually the desire to come up with some algorithms. So I will just leave you with those two criteria. Now, as I said, we were interested in developing algorithms for solving this realization problem, to which you pass the input-output equation and which give you the system in the state space form. So one important question in this regard is how many state variables do you actually need to do this? So how many axes do you need? Because if you don't know how many axes you need, there is no algorithm. You'll have to go over all possibilities for the number of axes, and there's infinitely many of them. But luckily enough, this does not happen in general. And this theorem tells us that if there is an irreducible differential polynomial of order h with respect to y, then if there exists some rational parameterization of this polynomial, then there has to exist a rational realization with exactly h state variables. So you'll need as many state variables as the order of your equation. And this is a reflection of a fact in classical algebraic geometry. So it all has to do with parameterizing corresponding hypersurfaces. And in classical algebraic geometry, we know that if you want to, if you have a unirational variety of dimension h, then you can always rationally parameterize it with exactly h parameters. You do not need more. And this theorem shows that in the presence of some differential conditions and the inputs, this does not fail. You can still develop an analogous statement. And so with those two criteria, so with those two propositions, which tell you how to reduce the realizability problem to the problem of parameterizing hypersurfaces, and with this theorem, which tells you how many parameters you actually need for that, we were able to do something algorithmically. So first of all, for an equation of order 0 with respect to u and of arbitrary order with respect to y, we were able to show that the realizability problem can be reduced to the problem of rationally parameterizing hypersurfaces in an n+1 dimensional affine space over K. So those propositions here tell you that you need to parameterize it, the hypersurface, over a fairly complicated field, and your parameterization has to be special. So it turns out that you can reduce finding this one special parameterization over a fairly complicated field to finding a set of rational parameterizations with no additional constraints whatsoever over a simpler field. So the complexity is in the fact that you would have to do this multiple times for multiple surfaces over K instead of just finding one special parameterization. And the second algorithmic result is that if you start from a first order equation, both with respect to u and with respect to y, and your coefficients are rational, solving the realizability problem over K is fully algorithmic. So you can fit this polynomial to a computer algebra system, and this will tell you whether it has a realization or not, and if it has a realization, it will give you some realization. So that's what happened for inputs. And as I said, if the order is greater than 2, algorithm with respect to u is greater than 2, doing something algorithmically in general is very complicated. Our intuition kind of fails. So we were unable to do something or anything at all with this. So now I would like to switch to talking about real realizations. But we will have to make a small detour, and I would like to motivate this detour now. So in general, I hope I have been able to show you that realizations come from rational parameterizations of the corresponding hypersurface. In Forssmann's case, it's fairly straightforward. When they're inputs, it's a bit more intricate, but there's still a way to recover any realization. So any dynamical system in the state space form from some rational parameterization of what's called the corresponding hypersurface. And it is also fairly straightforward to see that real realizations come from real parameterizations. And then suppose you want to find real parameterizations, real rational parameterizations of varieties algorithmically. And in the existing literature, with the existing knowledge in this subject, one has to start from considering a proper parameterization of the corresponding hypersurface. So the property of being proper means that you can invert the parameterization. So parameterization is a map from some affine space to a hypersurface, and it's rational. So if it admits a rational inverse from the hypersurface to the affine space, then the parameterization is called proper. And if a variety possesses a proper parameterization, it's called rational and not just unirational. And so it's important to be able to find proper parameterizations if we want to find real parameterizations. But proper parameterizations are interesting by themselves because they give rise to what's called observable realizations. And observability is a very important property in control theory. So if you give some system to a control theorist and ask them what kind of questions can you ask about those systems, one of the questions would certainly be whether it's observable or not. So I would like to, before switching to real realizations, talk a little bit about observable realizations and proper parameterizations and how those are related. And for this, we will need a piece of machinery. Let's say we will need derivatives. So suppose we have our system, our dynamical system in the state space form. So it's very simple, x prime equals p, y equals q. Now you can, for any rational function r, which depends on x's and then on u and on the derivatives of u, you can compute what's called the Lie derivative along sigma. And it's given by this formula, which might look scary at first, but really what's happening here is very simple. So you have your rational function r, it depends on x's and it depends on u. Now you kind of remember that x's and u's are functions of time. Those are our input signals and the state variables. And what you want to do is you want to compute the full derivative of r with respect to t. And to do so, you would naturally use the chain rule. And if you write down the chain rule for this function r, you would get precisely what's in the right-hand side here on this slide, with the only difference. You would replace pi in the first sum by xi prime. So you really just compute the partial of r with respect to xi times xi prime, and then the partial of r with respect to the u variables, and that's the second term. But now we have the system sigma, and our system sigma tells us what is x prime. It tells us that x prime is p. So in this formula for the chain rule, we replace x prime with p, and we get this expression for the Lie derivative, and that's precisely how it's defined. And I would like you to maybe keep in mind that this part of the Lie derivative that only depends on u's will be denoted du of r. We will need it in a couple of slides, but I will come back there anyways. So I promised to you that Forssmann showed that, well, yeah, I told you that Forssmann showed that you can really algorithmically go from a parameterization of the corresponding hypersurface to the to the realization of the differential equation, and vice versa. Now I will show you how to go vice versa, so how to go from the realization to the parameterization of the corresponding hypersurface. And this is done using those Lie derivatives. So first, you take the output, you take the function q that describes the output, and then you start taking the Lie derivatives along sigma iteratively of this q, and I claim that this will produce the parameterization of the corresponding hypersurface. And this will really vanish at the input-output equation. And I think there has been a question in the chat. So in the realization results, is there any way for optimization in terms of the control box for x, say bounds, in the choice of parameterization of the hypersurface? Yeah, that's a very curious question. I don't know how to answer this immediately, but a very good question. So in a sense, that there is a way to pick a very good parameterization, and that's what I'm going to talk about. You can start from a proper parameterization. This will give you the realization that kind of encodes all other realizations. Okay, so back to our corresponding parameterization. Again, how it works, you take the output and you take the iterated derivatives along sigma, and what you get will be called the corresponding parameterization. Okay. And we will call a realization sigma, so the system of F observable, if the corresponding parameterization is proper, that is, as I said, admits a rational inverse. And F will be called observably realizable if there exists some observable realization of F. Now, the first proposition I would like to share with you concerning observability is this one. So that's what I was trying to explain, that observable realizations are kind of the best. So if you take an observable realization of an input-output equation of order n, then every other realization can be found by reparameterizing sigma. Now, this means that you can just replace the x's in your observable realization by rational functions in some new parameters, say z. And this will give you a new system in a state space form with the state variables z. And I claim that in this way, you can obtain all possible realizations of a given input-output equation. So observability really is a nice property. And we tried to understand what it means to be observably realizable, again, for equations in small order. So in particular, if you start from an equation that has order 0 with respect to u and order at most 2 with respect to y, and it's realizable, then it's necessarily observably realizable. And this once again mirrors a classical algebraic geometry situation. So I told you that if you can rationally parameterize an algebraic variety, it's called unirational. And if there is a proper parameterization, it's called rational. And it's been an open problem for quite some time. Or it had been an open problem for quite some time, but the unirationality and rationality are really different. It turns out that they are not, but for curves and surfaces, they are. And curves and surfaces in terms of corresponding hypersurface correspond precisely to those equations of order at most with respect to y. So for them, unirationality and rationality is the same. And this translates into realizability and observable realizability being the same. And one more result is, again, when we allow higher order with respect to u, but low order with respect to y, we start from a realizable input-output equation of order 1, then being observably realizable is again equivalent to being realizable. And moreover, we can find observable realizations algorithmically if we start from a rational coefficient equation. And again, you can just feed it to a computer algebra system of your choice, write down a simple algorithm, and this will spit out a realization for you. So now we have talked about observable realizations, and we know how to find them algorithmically for the first order equation. And we will use this to find real realizations of first order equations algorithmically. So the first result I would like to share with you when it comes to real realizations is this one. This is the criterion for real realizability, which is not very constructive, but still, here it is. So we'll need this scalar vector z. So we start from P, which is a tuple of rational functions, which kind of are supposed to parameterize our corresponding hypersurface. And we want those functions to depend on here the derivatives, but just on x. We do not allow the derivatives of x. Then from this tuple, we can cook up the following z vector. So this looks a bit scary, and maybe it is, but anyways, you can write it down. You take the Jacobian of the first m components of your parameterization, exclude the last one, you invert the Jacobian, and you multiply it by this vector, which you can see here. So you take pi minus du of pi minus 1, and du is just this part of the derivative that depends on u. So it's not really important for general understanding what kind of vector z this is. It's just some vector. It can depend on u's axis and the derivatives of u. So the theorem says that if you have an irreducible differential polynomial of order n, then existence of real realizations of f is equivalent to the fact that the corresponding hypersurface V of f admits a real parameterization, so the one I required in the beginning of the slide, such that the first component is again independent of the derivatives of u, and this vector z is also independent of the derivatives of u. So in principle, it is extremely unclear how to check whether this very special parameterization with those properties exists. But it turns out that still it's a criterion that relates realizability over the real numbers to parameterizing hypersurfaces, and that's kind of the general spirit of those papers in this talk. And it turns out that you can actually still make some use out of it and do this algorithmically if you are in low order. So those two theorems kind of tell you that you can do this. So first, if you start with an equation with rational coefficients that has order 0 with respect to u and order 2 with respect to y, then if there exists an observable real realization, we can compute it. So the words observable and real here come together, and that's really important because we saw that realizability over an algebraically closed field is equivalent to observable realizability over an algebraically closed field for equations of this form. But this is no longer true with the reals. There can exist real realizations that are not observable, while there are no observable real realizations, while all observable realizations are meaningfully complex. And in the end, I will show you an example of this. And the second theorem says that if you have an input-output equation of order 1 with rational coefficients, then again, computing real realizations is fully algorithmic, as well as observed. So computing some realizations is algorithmic, computing observable realizations is algorithmic, and computing real realizations is again algorithmic. And you can really implement this without too much trouble. And I would like to spend the last 2 minutes or so of my time on motivating examples. It might be methodologically not very wise to put motivating examples in the end, but I hope you will forgive me for that. So the first example illustrates what I've just said, that you can have an equation that is defined over the reals that admits a real non-observable realization, and then no observable real realizations. So if you take this equation in particular of order 2, so this fits into this paradigm, into the conditions of this theorem. It has order 0 with respect to u and order 2 with respect to y. And still then no observable real realizations, but there is some non-observable real realization. And the final example is also kind of a motivating example for the second paper, let's say, and it shows you that you can start again from an equation with real, with rational coefficients, and it can be realizable over the complex numbers, but not over the real numbers. So in particular, if you take this lovely equation, it will have a complex realization. So x prime will really depend on this complex unit here, and y will be completely real. And the fact that only one of those components depends on I and the other one does not makes it impossible to kind of get rid of I by some smart coordinate change. So really no real realizations exist in this case. And I think this is it. This is it that I wanted to tell you. So thank you very much for your attention. I'm happy to answer your questions.
Okay, so thanks a lot for this really nice talk, Dmitrii. Do we have any questions or comments? Okay, so I see one question in the chat. Maybe I'll read it. So in the computational realization, are the real constants precise? And if not, how accurate do the approximations affect the observed variables?
Oh, yes. So those coefficients are precise. This was done using symbolic computations. So you can really symbolically parameterize things. Everything is absolutely precise. But then with the second, something that fascinates me and something that I would like to know, but I don't know. So you can really ask what happens if you like vary the coefficients of your input-output equation just a bit. how does this affect realizability? And how does the realization change, or does it disappear at all? And the answer is we don't know, but it's a really interesting research question, and I would be happy to know the answer. So I encourage everyone to think about this if you are interested.
Okay, any other questions or comments? Carlos, did you raise your hand?
Yes, I did. It's lower now. Thank you for a nice talk. I noticed that in some proper subset of your of the results, the input-output equation was assumed to be irreducible, or not. And I was hoping that you could comment a little bit on the role of irreducibility. Somehow one expects that it's enough to realize irreducible equations and somehow put them together at the end, but maybe instead it's some kind of serious restriction on when you can do things. So please illuminate us. Thank you.
Yes, thank you for the question. So this kind of brings us back to the definition of the canonical input-output equation. So if you start from some system and you eliminate and you do this differential elimination, you will necessarily end up with an irreducible input-output equation. So in particular, if you have a reducible one of the factors will be this irreducible equation that you want to consider. So you can really restrict yourself to irreducible equations and do nice real algebraic geometry with reducible hypersurfaces. So it does not really limit the generality at all.
Thanks.
Any other questions or comments?
I had another small question, if I may.
Sure.
You had this this interesting condition on a Jacobian matrix multiplied by a vector.
Yes.
Failing to have any derivatives of u appearing.
Yes.
I mean, you mentioned, I think, in passing that how to test this seems to be some sort of mystery, and I agree. But it's really tempting to try anyway. You know, like what would it mean for something like this to not have the u primes? You would like to maybe test this by, I don't know, evaluating at u equal to some constants, and then seeing that something doesn't change. Do you have any ideas about how to actually check this?
So not particularly, so not in general. So because to start from, you need some parameterization, right? And I told you that this, so this criterion, this theorem on the slide, it tells you that you need to have a very special parameterization for the realization to exist, right? But the problem is this problem comes from classical algebraic geometry. If the codimension of your, if the dimension of your if the dimension of your hypersurface is high enough, in particular if it's higher than 2, there are no algorithms whatsoever on how to compute any rational parameterization, let alone the special one. So it's really I have no idea here how to test this, because I have no idea how to test the thing that's in principle much simpler. Okay, and I think Bertrand also asked a couple of questions in the chat.
Yeah. May I ask, in the theorem that is being shown on the page, so you say there is a real realization of f if and only if the variety of f admits a real parameterization p and so on and so forth.
Yes.
Now, the condition that it realize a real realization of f is kind of independent of p, isn't it? In the sense that if it admits if this condition is true and it admits a real one, that would mean that that condition should be true for any p, isn't it right? All, I mean.
So, okay. Well, you can think of a parameterization p that, so you can just.
I mean the condition on p.
No, yes, I understand.
Yeah.
So I don't
depends on p, right? But the condition really shouldn't depend on any p in particular, right?
Yes, so I understand the question now. Let me try to answer this. Yes, so this theorem is very non-constructive in a sense that it is unclear how to check this. But if there is such parameterization, there is a clear way of how to recover realization from this P. Now you can, and of course this depends on the choice of particular P, because you can take some parameterization P, right, which satisfies all those properties. And then all you use, all the derivatives are actually in the coefficient fields. So you can multiply formally by u double prime all the components of the parameterization. And from this parameterization, you would not be able to recover anything. You would not be able to recover a realization. But of course, this comes from a parameterization that satisfies all those properties. And my claim is, the best answer I can give to that is that for any parameterization that satisfies such properties, there is a corresponding realization. So any parameterization that satisfies those two properties, such that the vector z does not depend on the derivatives, and such that itself does not, the first component of it does not depend on the derivatives. Any such parameterization will give rise to a realization. And in this sense, it doesn't matter which one you choose.
So does that mean that the real realization actually is dependent on P?
Yes, the one is, so the realization that you will obtain from the corresponding hypersurface depends on the parameterization of this hypersurface that you choose. So it always depends on the parameterization.
And then so it's also P depending on the realization, right?
Yes, vice versa. You can.
Yeah. So I think the theorem should actually state that relationship.
Okay. Yes, it's not very simple to put this into the statement of the theorem, but in the proof there is like a way to actually see how those are related. But yeah, I think that's a fair point.
Okay, thank you.
Okay, more questions in the chat if we still have time for this. I don't know. I can answer them quickly. They're very simple.
Sure. Go ahead.
Okay, so the first one is by Bertrand, and he asks, I'm a bit confused by the definition of an input-output equation. Can you determine whether a given algebraic differential equation is an input-output equation? Yeah, that's what this talk was about determining whether it is an input-output equation or not. So you can run those algorithms, and if you get a dynamical system that realizes it, then you're good. This is an input-output equation. If not, then not. So really, this is tied to the dynamical system that you start from. For each one, there is this unique canonical input-output equation. And if you want to know whether it is the input-output equation of some system, you really have to solve the realizability problem. So that would be my answer. And the second question is, could you please give the definition of unirational again? Thanks. Okay, so the variety X, in particular the hypersurface, defined by a single polynomial equation p equals 0, is unirational if it can be parameterized by rational functions. So suppose your polynomial equation is in variables x1 and xn through xn. So having a rational parameterization means having a set of functions, of rational functions, f1 through fn in like n-1 parameters, such that if you plug them into the equation P, this will vanish like almost everywhere. And then there is like some correspondence that you will recover almost all points on the, and then evaluating those functions f1 through fn at some values of the parameters will give you points of the variety. And this is a parameterization if you can recover almost any point on the variety by evaluating those functions. So I don't know if this was very clear or not, but that's, yeah. Basically, being unirational means having a rational parameterization for an algebraic variety.
Okay, if there's no more questions, then let's thank Dmitrii again for this really nice talk. And I'm looking forward to seeing everyone again in one more week. So I think there's one, okay, just a thank you in the chat. Okay.